Good morning, everybody. Welcome to our first online lecture on global climate change. Let's go. Okay, so the greenhouse effect. Let's start with this. The greenhouse effect is when wavelengths of energy break into an area, right? And those certain wavelengths of energy can be trapped inside of different types of molecules, right? And when that happens, that energy eventually has to be let out. And it's going to be let out in the form of heat, and that heat will be trapped inside of that space. These different wavelengths of energy include visible light, UV rays, X-rays, and gamma rays. And these wavelengths of energy, they can be reflected off of a surface, they can be transmitted through a surface, or they can be absorbed by something. Think about how the greenhouse effect is actually very well mimicked by your car in the summertime. Right? Let's say it's a hot day out. You go. It's time to go hang out with your friends at the mall or whatever you kids do. You open up your car and boom, it's like a freaking sauna in there, right? That's because your car is mimicking the greenhouse effect. What is happening is those UV rays from outside are transmitting through the windows, through the glass windows. And then when those UV rays hit the surfaces on the inside of your car, they get trapped by that material, right, by the molecules that make up the material on the inside of your car, and then that energy is let back out, but not in the form of UV rays anymore. Now in the form of whatchamacallit, heat, which we call infrared energy, right? Infrared wavelengths. But that heat, that can't transmit as easily as UV rays. So a lot of those infrared wavelengths of energy, they end up staying trapped inside of the car because it can't transmit through glass as easily as UV rays. So that's what the greenhouse effect is, right? But this also works on a larger scale, like with the Earth. But more on wavelengths of energy first. So right, you have your I wonder if you guys can see my mouse. I guess we'll find out. You have your gamma rays, your X-rays, UV rays, your visible light, which is what we can see. Infrared rays, right? For those of you that play Call of Duty, you can attach an infrared scope to let you see the heat signatures on your enemies, right? This is light that we can't see with our eyes, but we can see with special equipment. You have microwaves and radio waves. And this visible light here ranges between 380, the NM stands for nanometers, so 380 nanometers to 750 nanometers of space between those waves. And we can relate this, earlier on, I mentioned how materials can absorb UV rays. Well, different molecules can actually absorb the energy of a vast amount of different energy waves. And some materials absorb certain energy waves better than others. For example, if you take plants are really good at absorbing blue light here, right? I don't know if you noticed, but down here you have the same wavelengths of energy as you have up here, right? So 380 nanometers, 380 nanometers nanometer long wavelengths are your purple rays, whereas up here your 750 nanometer wavelengths of energy are your red, is your red light, right? And everything in between. So, and the gray line here is the absorbance of the chlorophyll, right? And the green is the rate of photosynthesis. And okay, so based on this graph, we can see that plants are really good at absorbing blue light here, right? And also very good at absorbing green light. And they're moderately okay at absorbing violet through blue light, but they're really bad at absorbing light blue through yellow light, which, you know, makes up the green spectrum. And so it's no coincidence that when we look at grass or leaves or most plants, they appear green. They appear green because they don't absorb that light. They reflect it. But other things absorb different types of light, like let's think about, what about I don't know what the hell. Think about natural things that absorb cardinals, right? So the feathers on cardinals are red because they just don't absorb red light. So just another example of something. All right. Anyway, let's talk about that same concept, but with we'll get there in a second. Let's go over this real quick. So what happens when something absorbs that energy, especially with UV rays, is when it traps that energy in the form of a UV ray, right? This yellow light will be our UV ray. The atom, the electron on that atom will absorb that energy, and it will actually move up to a higher energy level on that atom. Hopefully you guys remember all of this stuff from your 9th grade year. And it makes a quantum leap up to a higher energy level and starts spinning really orbiting the nucleus a lot faster. And then eventually, though, that energy has to be released. And when it releases that energy and moves back down to a lower energy level, it releases that energy in the form of heat, which is how the greenhouse effect is created. That's how heat is created from sunlight, from UV rays. And pretty much everything that I just said is written right here. Objects that absorb shorter wavelengths of or higher energy rays from the sun usually warm up, and when they cool down, they usually radiate that energy as longer, lower energy wavelengths, like infrared heat. Our skin absorbs infrared heat, and that's why we feel it. Our skin also absorbs UV rays. That's how we get sunburn, right? But our skin is much better at absorbing infrared wavelengths of energy, infrared heat or infrared energy, and that's why we feel it more immediately than we do sunlight. Much of the incoming energy from the sun is absorbed by the ground, warming it up, and then when it cools down, it radiates infrared energy back out towards space. And so the Earth must radiate or reflect about the same amount of energy that comes into our atmosphere from the sun back out into space, or else the Earth will gain more and more energy, causing it to heat up. So the Earth has to, it has to maintain homeostasis. It has to get rid of just as much heat as it absorbs. Otherwise, it's going to get hotter and hotter and hotter if it retains more and more of that heat. And that's what's going to cause global warming. What is causing global warming. Anyway, we're going to go more into that in a second. There's a bunch of gases in our atmosphere, right, that allow higher energy wavelengths from the sun, like UV rays, to pass through, but they absorb lower energy wavelengths of energy, like infrared rays that come from the ground. And those gases are called greenhouse gases, right? Carbon dioxide, methane, are the two strongest, and water vapor. Now, without greenhouse gases, our planet would be too cold. We have to have them. Greenhouse gases are a good thing. If we didn't have carbon dioxide, if we didn't have water vapor, if we didn't have methane, then our planet would just, since the beginning of time, be a big ball of ice, and we wouldn't be having this conversation right now. But that's not the case. They're there, and so we're here. Okay, so the greenhouse effect is what keeps our planet warm enough for life, right? Here's a picture describing that whole process. You have a lot of UV rays coming in from the sun. Some of that is reflected by the ozone layer or clouds or what have you. A lot of them, though, is transmitted through the atmosphere, and then they hit the ground. And when they hit the ground, that material retains that energy and then releases that in the form of heat. A lot of that heat is supposed to be leaving and transmitting through the atmosphere back into space. And then some of that heat should be absorbed and retained, so that we can have enough heat for life. What the problem is that less and less of that heat is being transmitted, and more of that heat is being retained. That's an issue. So here's all of our gases that make up the atmosphere: methane, nitrous oxide, oxygen, and ozone, carbon dioxide, and water vapor. And here's all of those gases together that make up the whole atmosphere. You have your infrared energy, which is greatly absorbed by water vapor, right? And not as much as by carbon dioxide and oxygen and nitrous oxide and methane. But this is a good thing. We want infrared to be absorbed. If it's absorbed, then it's kind of like it's how do I put this? It's kind of like it's if it's absorbed, it's not felt. It's not actually warming other things up. It's kind of like a buffer, right? This is a good thing. If it's not absorbed, like methane up here, methane does not do a great job at absorbing it. Methane actually, takes in those UV rays and then heats up and releases that energy back out. And because it doesn't do a good job of absorbing that infrared energy, a lot of that heat is what heats up the rest of the world, right? Same thing with carbon dioxide. Now, see, carbon dioxide is actually not as strong as a greenhouse gas as methane. Methane is the strongest greenhouse gas. But the thing is, there is so much more carbon dioxide in the atmosphere that it is more of a problem than methane. But anyway, and then you have your UV light, which is greatly absorbed by oxygen, right? Which is a great thing. That's why our ozone layer does a great job of protecting us from UV rays. And so do clouds, right? A big component of clouds is oxygen. Well, clouds are actually just water. It's really just water vapor, but they also do a great job at reflecting and absorbing those UV rays too. We're gonna come back to this graph later on. Oh, that thing on the bottom there. So these waves, that's just demonstrating what the length of the waves are at a certain energy level, right? So UV rays are short energy rays, low level, and infrared rays are longer, and they're a higher energy ray. All right. I don't need to go over that again. So that's the science behind global warming. That's what is on a molecular level, that is what is causing the atmosphere to warm up, and that's causing global climate change. So it's been about 15 minutes. I think I'm gonna stop there, keep it short, and we'll go over global climate change next time. All right, peace out, bros, and sister. Okay.